This video will start the problems on continuity, which starts on page 64. And on page 64, I will start off with example number 3. Now, even though these are continuity questions, most of the techniques that we'll be using to solve these problems are very similar to all the previous lessons. So for question number 1, let f be defined by this rational function here. And I want to determine all values of x where f is discontinuous. So when we're looking for discontinuous properties, we're looking for vertical asymptotes and holes, right? If you have vertical asymptotes or holes in your graph, then you have to lift up your pencil in order to draw the graph. And in high school, we kind of say that if you have to lift up your pencil, then the function is not continuous. Okay, so let's jump right into this. I will start by rewriting the problem out. I will write out, f of x equals to 2x plus 4 over 4 minus x squared. And right away we can probably factor the numerator and the denominator. Let me just get rid of that. And if I factor the numerator, I get 2 onto x plus 2. And on the denominator, I get 2 plus x and 2 minus x. Now, you don't want to jump to canceling things out or anything. We're trying to find values where x is discontinuous. So over here is discontinuous when x equals to negative 2. And over here is discontinuous when x equals to positive 2. And you can definitely say that these two expressions right here, they cancel off. So this right here is your hole, and this right here is your vertical asymptote. So the values of x where you're discontinuous are x equals to plus or minus 2. Okay, let's move on to part 2 now. Part 2 says find the equations of the vertical and horizontal asymptotes. Okay, so for this question here, we want to rely on our pre-calculus 11 knowledge, and the vertical asymptote, well, we already found it in part 1, so the vertical asymptote happens when x equals to 2. Now for the horizontal asymptote, if your original problem is y equals to 2x plus 4, and on the denominator, I'm just going to rearrange the expression to be negative x squared plus 4. If you have more, if your degree is higher on the x on the denominator compared to the numerator, then from pre-calculus 11, your horizontal asymptote is defined to be at y equals to 0. So whenever the denominator has a higher power of x compared to the numerator, the horizontal asymptote will always be at y equals to 0. All right, let's move on to question number 3 now. For question 3, if I can get it here, find the limit of find the limit of f at each discontinuous points. So going back to part 1, our discontinuous points were x equals to 1 and x equals to, not 1, sorry about that, it was actually 2 and negative 2. My bad, I'm just kind of thinking about a different problem right now. So it should be negative 2 and positive 2. Alright, so now we need to find the limit at each of these discontinuous points. So what we're doing is we're asking you now to find the limit as x approaches negative 2 of the original function, and we need to find the limit as x approaches positive 2. Alright, so just follow the instructions on what the question is telling you to do. If this is your discontinuous point, find the limit at those points. I will go ahead and do this one first. When x approaches negative 2, that limit is a little bit easier to solve because it's just a few steps. So x approaches negative 2. Now your original function was 2x plus 4 over 4 minus x squared. Once again, we can factor this out. And the denominator will be 2 plus x and 2 minus x. This is the limit as x approaches negative 2. And then we can solve this problem like we did back in the first few lessons. And if I do that, I get the limit as x approaches negative 2 2 on the numerator, the denominator will be 2 minus x, and then we can go right into a direct substitution step here. So this is -2, so let's plug in -2 for the denominator there, and if I'm doing a substitution step, I don't need to write out the limit sign. So this will be 2 over 2 plus 2, which is 1/2. Alright, so that's one limit right there. Now we need to find the limit as x approaches +2. Okay, so let me just move this over here if I can. Alright, so if I go ahead and now finish this limit will be the limit as x approaches 2. Now the original function was 2x plus 4 all over 4 minus x squared. I remember there was, let's just skip a step here because we already did most of these steps in the previous question. So I believe if you simplify everything, you're down to this expression, 2 over 2 minus x. Okay, so in order to do this limit right here, you can't really do any more factoring, you can't times by the conjugate, and you'll notice that if you plug 2 in for x, you get the vertical asymptote. So now this is a one-sided limit problem. So in order to evaluate this limit now, you have to take the limit as x approaches 2 from the right-hand side and the limit as x approaches 2 from the left-hand side. So, these questions, I do believe we covered quite a bit of them in the previous lessons, but it's just tedious that these questions make you do multiple limit statements, which requires you to do quite a bit of algebra here. Now, I'm going to draw a number line over here right below this green box. Let's go ahead and plug 2 in the middle. And on the left-hand side, let's plug in 1.9, and on the right-hand side, let's plug in 2.01. And we're just checking to see if the numerator and denominator are positive or negative. So if I take 2.01, which is on the right-hand side, and if I plug it in to the right-hand limit, I should get this. And the numerator is positive and the denominator is negative, giving you negative infinity. And if I go ahead and plug in 1.9 in for the left-hand limit, I get 2 over 2 minus 1.9, and I get a positive on the top and a positive on the bottom, and we get positive infinity here. Since these two limits, since they're not equal to each other, the limit as x approaches positive 2 of f of x, it does not exist. Okay, so quite a bit of work, but I think a lot of the steps we've seen already in previous questions. All right, let's move on to the next one. All right, let's move on to question number 2 on page 64. So we have another similar problem. The rational function is a little bit different, but let's see if we can approach the same kind of questions again for these discontinuous continuity problems. So for part 1, determine all values of x where the function is discontinuous. All right, so discontinuous in our course, those have to do with vertical asymptotes and holes. And when we're dealing with rational functions, it's very common to get those properties. Alright, so my recommendation for this problem is let's go ahead and factor the numerator and the denominator. So if I factor the numerator, I get 2x plus 1 and x minus 1, and the denominator will be x plus 1 times x minus 1. Now, you don't want to go off and start canceling things off. This part right here means you have a vertical asymptote at x equals to -1. And since these two terms, they technically do cancel off, that means you have a hole at x equals to +1. So the values of x where you're discontinuous, they're at x equals to -1 for your vertical asymptote and at +1 for your hole. So x equals to positive and -1 is your answer for question number 1. We went to question number 2, find the equations of the vertical and horizontal asymptotes. Okay, sorry, let me just get this settled here. Okay, so your vertical asymptote, we already know from the first question. Your vertical asymptote is at x equals to -1. And if I go ahead and write the original problem again in factored form, it was 2x plus 1 onto x minus 1, all divided by x plus 1, x minus 1. Those terms cancel off. and now you have 2x plus 1 over x plus 1. Now going back to your pre-calc 11 concepts, if the power of x in the numerator is the same as the power of x in the denominator, then your horizontal asymptote is the coefficients in front of the x variable. So the coefficient in front of the denominator, in front of the x term, is a 1, so 2 divided by 1 is 2, so the horizontal asymptote is at y equals to 2. So there's your horizontal asymptote there, and there's your vertical asymptote there. Done. Let's move on to question 3 now. Find the limit of f at each discontinuous points. Alright, so our discontinuous points were x equals to positive 1 and x equals to negative 1. That's based on the results from question number 1. And what we need to do now is we need to find the limit as x approaches positive 1 of f of x. And we also need to take the limit as x approaches negative 1 of f of x. Okay, so what I'll do first is I will find the limit as x approaches negative 1, because that one might be a bit easier, who knows. So if I do that calculation here on the side here, the limit is approaching negative 1, and my original problem was in factor form this, all over x plus 1, x minus 1. And now let's go ahead and actually cancel out the terms. So now I have 2x plus 1 all over x plus 1, and I have the limit here as x approaches negative 1. Okay, so unfortunately there are no nice ways to finish off this problem, because if you're plugging in the negative 1 into the x, you get the vertical asymptote. So just like the previous question, this is a one-sided limit now, where you need to find the limit as x approaches negative 1 from the right-hand side, and the limit as x approaches negative 1 from the left-hand side. And I will put a 2x plus 1 there, and an x plus 1 there, a 2x plus 1 there, and an x plus 1 there. So let's go ahead and set up a number line with negative 1 in the middle here, and on the left hand side we'll pick a number, and on the right hand side we'll also pick a number. So maybe negative 0.9 there, and negative 1.1 on the left hand side. If I go ahead and substitute these values into the right hand side, I would get 2 times negative 0.9 plus 1 all over negative 0.9 plus 1. And then all I have to do now is I need to figure out whether the results are going to be positive or negative. Alright, so the numerator will be negative, and the denominator here will be positive. So my final result here is going to be negative infinity. Alright, let's move on to the next one. If I pick negative 1.1 on the left hand side and plug that in for my x's, I would get 2 times negative 1.1 plus 1 all over negative 1.1 plus 1. And if I do that calculation here, I get negative on the top, negative on the bottom, and I get positive infinity as the final result. So that limit does not exist. Okay, so the limit as x approaches negative 1 does not exist. Okay, unfortunately I do need to erase a lot of this now, because I need to actually do the limit for the next x value that's discontinuous, which is not continuous, sorry, and that's at x equals to positive 1. I hope that one will be a little bit easier, but who knows with these limit problems. They always require quite a bit of work and algebra and setup. Okay, so let's go ahead and figure out this one now. So that's the limit as x approaches positive 1. Now let's go ahead and just get the factored form here, which is 2x plus 1 all over x plus 1. So I'm not going to show all the factoring steps, and indeed this one's a bit easier, because if I plug in the values of 1 for x for direct substitution, I get 2 plus 1 on the numerator and 1 plus 1 on the denominator. Final answer is 3 over 2. Great. So just to summarize here, the limit as x approaches 1 of f of x, that was 3 over 2, and the limit as x approaches -1 of f of x, that does not exist. All right, so a little bit of work there, and hopefully you guys can figure out or be okay with that. Okay, let's move on to the next page. We're now on to page 65, and for page 65, we have a piecewise function, and in this question we now need to use the three-part definition of continuity to prove f is continuous at x equals to 2. Now, for the three-part definition of continuity, in class it was discussed that the first part of the definition is f of a is defined. Now, if you're wondering what a is the value that's given to you in the restriction part of the piecewise function. So if you look at my piecewise function, the problem is centered around 2. Either you're less than 2 or greater or equal to 2. And since these two values are, the points that separate the graph, a actually has a value of 2 in this case. Okay, now for part 2, the definition, we have to ensure that the limit as x approaches a of f of x is defined, or it exists. So that means the left-hand and right-hand limits are equal. And then for the third part, we need to also show that f of a is equal to the limit as x approaches a of f of x. So that was the three-part definition. If you do all three of those things, then you've shown that the function is indeed continuous. And if you graph it, you should be able to draw it without lifting your pencil. Okay, let's go ahead and attack the first part of the definition. F of a is defined. So for part 1, like I said, is f of 2, is this defined? Okay, now if you look at your piecewise function, 2 is defined at this part of the piecewise function because it actually equals to 2. So you're looking at this part of the graph right now. So f of 2, you just plug in 2 for that quadratic right there. This will give you -4 plus 6, which equals to positive 2. Alright, so we're actually done now for part 1. So if I go back to my list here, I can say that f of a, or f of 2, equals to 2 in this case. Alright, so this 2 right here is that 2 right there. And this 2 right here is this 2 right there. Alright, so hopefully the letters are okay for you. Alright, let's move on to the second part of the definition. I'll erase the first part now. I don't need... Okay, so I'm just going to erase the first part of the definition. Alright, so for the second part of the definition, I need to see if the limit is defined or if the limit exists. So if I plug in the numbers now, I need to see if the limit approaches 2 of f of x. Does it actually exist? Alright, so what that means is I need to take the limit from the left-hand side and the right-hand side. So in order to evaluate this limit, I need to do this limit first, which is the limit as x approaches 2 from the right-hand side. And the right-hand side is this guy, so that's -x squared plus 6. And once again, this is similar to part 1, it's just a direct substitution question. So negative bracket 2 squared plus 6, and then we got 4. So the right-hand limit is 4. And for the left-hand limit, I'll do that part in green. As x approaches 2 from the left-hand side, now we're dealing with, let me just erase this. Alright, so now we're dealing with this part of the graph. This negative sign means we're approaching the left-hand side. So now we're dealing with this part of the graph, which is 3 over x plus 1 plus 1. Let me just erase that. Okay, so with this question here, we can just do a direct substitution now. Let me just change colors to red now. So I circled my 2 here, plug that in. This will be 3 over 2 plus 1, and then plus 1. So this will be 3 over 3, and 3 over 3 plus 1. So that's going to be 1 plus 1, which equals to 2. Okay, so the problem here is the left-hand limit equals to 2, and the right-hand limit equals to 4. So that means we technically did not satisfy condition number 2. Alright, so since condition number 2 doesn't work for this problem, because the left hand and right hand limits don't work, we can say that the function is not continuous. And once we show that the function is not continuous, we're done the problem. Alright, time to move on to the next one. Alright, another classical question here. Find the